last general module about reactions before you dive into specific reactions of different functional groups. Um, and so I want to talk about the concept of oxidation and reduction. Um, this is kind of a general concept that comes up in general chemistry. You may have seen it in an earlier chemistry class, you may not have. Um, and like many things in organic chemistry, we are going to take a simplified approach um, rather than a very rigorous approach to treating oxidation or reduction, because it can be helpful when you see a reaction to identify if a molecule has been oxidized or reduced. That gives you an idea of the kinds of reagents you might use to carry out that reaction. So, if you haven't heard the terms before, oxidation, that term comes from the fact that oxygen is very electronegative and tends to take electrons away from things. So, when things lose electrons, we tend to call that oxidation. Um, when something loses electrons, its charge goes up. So, it could become, it could go from neutral to +1, +2, +3. So oxidation is associated with the charge on an atom getting higher. Um, Reduction then makes sense because when something gets reduced, its charge goes down. It might go from +2 to +1, or +1 to 0, or 0 to -1. So when we say things are getting reduced, that means their charge is going down. So I've written this out kind of explicitly in these notes. So when we talk about things being oxidized, we're talking about them losing electrons. And generally, when things are losing electrons, they don't necessarily get a charge of +1, but when they're bonded to something more electronegative, it's sort of like they're losing some electron density. And that's what we consider oxidation. So usually oxidation is occurring when something's bonding to a more electronegative atom. The mnemonic that is often used for this is losing electrons is oxidation. So Leo, um, and you may know that Leo is Latin for a lion. Um, so what does a lion say? Well, a lion says grr. So Leo the lion says grr. Gaining electrons is reduction. So when something gains electrons, usually by bonding to something less electronegative, we call it reduced. And its oxidation state goes down. You may have encountered this before, you may not have. In a general chem class, you might have seen reactions like this, where we have aluminum reacting with copper chloride, um, making aluminum chloride and copper. This is sometimes called a single replacement reaction. This reaction would be known as a single replacement. Um, that description doesn't necessarily give us a good idea of what's going on in the reaction. So I'm not a huge fan of that term, but it may be familiar to some of you. What's really going on here, if we examine the charges on the atoms and the ions, is that electrons are getting transferred. So if I consider my aluminum when I start, it's just aluminum solid. That solid aluminum really has a charge of 0. But when I consider the product, aluminum chloride, that's now dissolved, that's really made of aluminum 3 plus ions and then 3 Cl minus ions. So notice that the aluminum has gone from a charge of 0 to a charge of 3 plus. We would say aluminum is oxidized because its charge is going up. It's losing electrons. Um, at the same time, Copper starts out in this copper 2 chloride. Its charge is 2 plus. Copper 2 chloride is Cu2 plus and 2Cl minus ions. Whereas when it's done, it has a charge of 0. So copper is gaining electrons. It's going from +2 to 0. So we would say copper is reduced in this case. So that's the idea with oxidation or reduction. If you've taken a class like AP Chem, or if you take a Gen Chem class in the future, you might see more complicated oxidation reduction reactions like the one I've written below. In this one, we can see that iron goes from a charge of +2 to +3. So we could say that iron is oxidized. That one is more straightforward because we can just see the charge increase. On the other hand, if something is losing electrons, like iron is losing electrons, it has to be giving those electrons to someone else. And in this case, it's giving those electrons to manganese or Mn. That might not be obvious to you. There is a set of rules that you can use to assign what we call oxidation state. Some of those rules can be complicated, so I'm not going to go into them in detail. But if we were to apply those rules, what we would see is manganese at the start of this reaction in MnO4 minus. This has an oxidation state of +7, whereas at the end it has an oxidation state of +4. So manganese is reduced because its oxidation state goes from +7 to +4. That's going down. It's getting extra electrons. If that part doesn't quite make sense to you, don't worry about it, because like I said, in organic chemistry, we're going to use much more simplified rules. So I'll explain what those are. But if you have seen examples like this before, I just wanted to give you a reminder. We will not talk about oxidation state. Oxidation state is very formal and has these complicated rules. We're going to talk about what we call oxidation level of carbon. It's a closely related concept, but it's a little simpler. Okay, so that's the groundwork, and next we can dive into what we mean when we talk about oxidation level in organic chemistry. Okay, so let's get into the specifics of what we mean when we talk about oxidation level of carbon atoms. So carbon can be bonded to less electronegative atoms. It can be bonded to more electronegative atoms. When we talk about oxidation level, we're generally talking about how many bonds does it have to more electronegative atoms. All right. And because carbon makes up to 4 bonds, essentially that gives us 5 oxidation levels that are possible. It can be bonded to 0 more electronegative atoms, or 1, or 2, or 3, or 4. So those are our 5 oxidation levels that we'll deal with. Most of the time, we'll be in the 1 to 3 range. In a typical chemistry class, you will see 0 and 4 from time to time. One little quirk. So we start by counting the number of bonds between carbon and atoms that are more electronegative. Sometimes we have pi bonds between carbon atoms. Those we're going to count as half a level for each of the carbons. Okay, so let me look at some examples. The lowest oxidation level would be alkanes. Alkanes are just carbon and hydrogen. There are no more electronegative atoms there, so there are no there's nothing to make those carbon atoms oxidized. Um, if we look at level 1, those would typically be things like alcohols or um, alkyl halides. Notice if I'm counting number of bonds to more electronegative atoms, this carbon here has an oxidation level of 1 because it's got 1 bond to more electronegative atoms. And that's how we decide that an alcohol or an alkyl halide is at oxidation level 1. Um, an alkene is a little more complicated because an alkene has 2 carbons that are each bonded to, each has a pi bond to another carbon. And we said those are each going to count as 1/2 of an oxidation level. Because each of those is 1/2 oxidation level, we would say the total oxidation level is 1. Similarly, for alkynes, each of those has 2 pi bonds to another carbon. So each of those has an oxidation level of 1, and 1 plus 1 equals 2 for the total oxidation level. And that's why an alkyne would be considered to be on the same level as an aldehyde or ketone, or some of these other functional groups where you've got 2 bonds to more electronegative atoms. So these each have 2 bonds to more electronegative atoms. That puts them at oxidation level 2. And then we have our carboxylic acid oxidation level, where we have a carbon bonded to 3 more electronegative atoms. So you'll notice we give an oxidation level name. So each oxidation level is typically referred to as derivatives of that most common functional group at that oxidation level. So at oxidation level 3, it's a carboxylic acid is the most common. So the rest of them are called carboxylic acid derivatives. At oxidation level 2, they're ketones and aldehydes. Those are the most common oxidation level 2 functional groups. That's all that we mean when we list this oxidation level name. So our highest oxidation level possible would be when carbon has 4 bonds to more electronegative atoms. That would be things like carbon dioxide, or this compound over here. This is called carbonic acid. And derivatives of that are often called carbonates. So those are our main oxidation levels. What we're going to do is track in reactions when an atom moves up in oxidation level or moves down in oxidation level. So generally, applying our terms, when something is moving up, we would say that's oxidation. Or we would say that carbon is being oxidized when we're moving up this list. When we're moving down this list, that's when we say carbon is being reduced. So you might hear a chemist say, oh, I need to reduce this ketone to an alcohol, right? That would be a typical statement you might hear from a chemist. We could say, I'm going to reduce my ketone to an alcohol. You also might hear a chemist say, oh, I need to oxidize this aldehyde to a carboxylic acid. And that would be moving the other direction. So that's just introducing you to the kind of language that you'll hear around oxidation level. Um, and when you see these reactions, I just want you to be familiar with the language and understand it's not anything super special. It's just we're counting bonds to more electronegative atoms. So that's the overview of oxidation levels of carbons. Um, so next we'll look at how we track oxidation level in reactions and some of the general ideas to keep in mind when we're thinking about how oxidation level changes during a reaction. So let's talk about oxidation and reduction reactions. Um, Generally, we'll see a lot of reactions that are not oxidation or reduction. So reactions that stay within the same oxidation level. So here's an example. I start with a carboxylic acid. Notice that a carboxylic acid has 1, 2, 3 bonds between carbon and oxygen, which is more electronegative. So this is oxidation level 3. And an ester also has, from that carbon, 1, 2, 3 bonds to oxygen. So 3 bonds to more electronegative atoms. So this is also oxidation level 3. When we see reactions that look like this, they are usually, not in every case, but they're usually reversible. Um, and their mechanisms are things that we can understand using the curved arrow formalism that you've seen so far. Um, and most often, what's interesting and useful about these is that once you've identified that you're staying within the same oxidation level, you can think about the forward and reverse reactions, and they generally go through the exact same intermediates. Meaning, if you can draw the forward reaction and you can identify what the different intermediates are along that pathway, then for the reverse reaction, you'll see the exact same intermediates. In most first year organic chemistry classes, these are going to be reactions where you will practice these mechanisms over and over. So let me give you an example from the next 2 slides of what I mean. So here is the mechanism for that same reaction drawn out. Okay, so this is that reaction where we're taking a carboxylic acid and turning it into an ester. This reaction is known as Fischer esterification. Organic chemists love to name reactions after people. So you'll often encounter reactions that have names. This one's called Fischer esterification, not a name you need to know, but just pointing that out. So in my mechanism, I see that there's an H plus catalyst, meaning we've added some acid to our mixture, and that acid is going to act as a catalyst. You may or may not have encountered that term before, but a catalyst is a substance that speeds up the reaction but doesn't get used up in the reaction. Um, and when you encounter a catalyst in a mechanism, essentially that catalyst has to get regenerated at the end of the mechanism so that it's still there. The useful thing about a catalyst is if you just add a little bit of it, it can help a whole lot of molecules through the reaction because every time the reaction happens, we regenerate the catalyst and allow it to go speed up the reaction again. Um, when we encounter H plus catalysts, generally that means we've added some acid and those extra H pluses are going to be bonded to our solvent. In this case, our solvent is methanol. So the H plus that we start with is going to be bonded to methanol. So I've asked you to practice filling in the curved arrows for each step in this mechanism. Okay, I'm going to work through the first one with you. Then I'm going to ask you to pause the video and work through the rest on your own. This is good practice, just practicing those curved arrow skills that you learned in Module 11, Module 12, Module 13. So in my first step, I see that I've created a new bond between that double bonded oxygen and a hydrogen. I've also shown that I have an extra hydrogen bonded to methanol, so it's methanol with 2 hydrogens and a positive charge, and then it's losing one of them. So I know that I'm going to need a curved arrow that creates that new bond. I ask myself, who has the electrons to form that new bond? Who's going to share electrons to make the bond? That's going to be the oxygen. Hydrogen doesn't have any electrons of its own, so it needs to be the oxygen that has a lone pair, and it's going to share that lone pair with this hydrogen. That's going to break that hydrogen-oxygen bond, and that's going to give me my, now what I would call a protonated carboxylic acid, because I've added a proton to it. So at this point, I'd like you to pause the video, go ahead and draw your curved arrows for each of the subsequent steps. Once you're done, resume the video, come back, and I'll walk through it all. All right, in my second step, I see that my methanol molecule is now bonding to the central carbon in my carboxylic acid. That means I'm going to need to take a lone pair on this oxygen, and I'm going to need to share it with the central carbon. That's going to break that double bond. That'll give me this next intermediate. In the next step, it seems what I'm doing is just taking off a hydrogen. We would call this deprotonating. So I'm going to use one of my solvent molecules to go ahead and deprotonate that oxygen. And then the next step, it looks like all I've done is protonated a different oxygen. So what I'm going to do is use a lone pair from that oxygen to go and grab an H plus for my solvent. And the next step is maybe the trickiest. In this case, I see that I am breaking my molecule into two because I have two products coming out of this step. Water is a byproduct. So I need water to leave my molecule. I see down here that I've got H2O. So I need this bond to break to make that H2O. That's going to become the water. That's a byproduct of the reaction. But I also need to form a double bond. So I ask myself, who has electrons to share to form that double bond? That would be the oxygen here. So I'm going to push these electrons down, share them with the central carbon, and push the water out. And then my last step appears to be just a deprotonation where my solvent is taking H plus away. That gives me my final product. Notice that regenerates my protonated solvent, that regenerates that catalyst. So that is the mechanism for the forward reaction. On the next slide, what you're going to see is the reverse reaction. And I took all the same intermediates, and I've already drawn them out. I just reversed the arrows to show the direction of the reaction. And what I'd like you to do is pause the video and try and draw the curved arrows for each step in the reverse mechanism. Again, this is good practice with your curved arrow skills. So pause the video, come back once you've drawn these, and I'll walk through them. Okay, hopefully you have filled in these curved arrows yourself. But going in the reverse, we're going to see a lot of the same steps. So in the forward reaction, the last step was to deprotonate. In the reverse reaction, the first step is going to be to protonate. So that carbonyl oxygen, that double bonded oxygen, is going to go grab a hydrogen. In the second step, this is where I need to have the water come in and add itself to that central carbon. So water has a lone pair. It's going to share that lone pair with the central carbon, break the double bond. That gets me to this intermediate. Now I have a proton here that I need to remove. And then in my next step, I need to add that proton just to a different oxygen. So this oxygen is going to go share its lone pair with hydrogen. This next step, this is that one where I need to kick out a molecule. If you go a little deeper, this is a step that I would call a lone pair push. If you make it to a module where you're talking about reactions of carbonyl compounds, this is where I'm going to share this lone pair with the central carbon to make the double bond. And at the same time, I'm going to push out this methanol molecule that in the reverse reaction is a byproduct. So this methanol here is the methanol that we would produce in the reverse reaction. And then my last step is just to deprotonate. Okay, so that was an exercise to just show that when we're dealing with reactions within the same oxidation level, we generally have mechanisms that we can go back and forth using similar conditions and following similar mechanisms with the same intermediates. So that was the point about these reactions within the same oxidation level. Reactions that change oxidation levels, so oxidation reactions or reduction reactions, most often these are irreversible, or these are reactions where if you want to go in one direction or the other, you need to use very different reagents and the mechanisms will be entirely different. So notice for this first reaction that stays in oxidation level 3, I used an acid catalyst and just added a little different other compound to make the reaction go one way or the other. To make it go forward, I added methanol. To make it go in reverse, I added water. If I want to take a ketone and turn it into an alcohol, this would be a reduction, right? So when I'm going this way, this is reduction. I would say I'm reducing that ketone. I use a reagent called NaBH4, sodium borohydride. Ethanol here is playing the role of solvent. That's one set of reagents. If I want to go in reverse, if I want to take an alcohol and turn it into a ketone, that's oxidation. And to carry that out, I'm using a different reagent. In this case, CrO3 or chromium trioxide with water. Those are two very different reagents. Um, we give these things names. When things are reduced, the reagent we're using is generally called a reducing agent. Reducing agents tend to be things that are going to give away electrons. If you're going to give away electrons, they usually have less electronegative atoms like boron or aluminum or magnesium. Um, these atoms with low electronegativity that are more willing to give up electrons. Often reducing agents have hydrogen atoms in them as well. Um, so we're adding hydrogens in bonds to hydrogens in place of bonds to more electronegative atoms. So for example, in this case, in the forward reaction, I'm adding a hydrogen to the central atom. That's taking the place of an oxygen. So that's why the oxidation level goes down. Oxidizing agents are things that tend to take away electrons. So they usually have lots of electronegative atoms like oxygen. Um, so CrO3 is a good oxidizing agent for that reason. Now, when we look at the mechanisms for these, and these mechanisms might be less common for you to learn in a first year organic chemistry class, um, these mechanisms will be entirely different. So let me show you what the two mechanisms look like. They're both on this slide here. And if you look at them as an overview, there is nothing in common between these two. The intermediates are entirely different, and the outcomes are entirely different. I did fill in the intermediates for you, so for practice, you can go ahead and fill in the curved arrows for each of these. Again, I'll ask you to pause the video, come back once you've drawn the curved arrows, and then see how you did, and let me know if you have questions. Okay, now I'm going to fill in the curved arrows for these mechanisms. For this first one, this reduction using sodium borohydride, we've seen before that when we have compounds involving things like sodium, remember these are going to split up into ions. So I get Na plus and BH4 minus. Na plus in this reaction is essentially just a spectator ion, meaning it's not playing an important role in the reaction. It's really the BH4 minus that serves the most important role. So in this first step, I notice that I have added a hydrogen to the central carbon. That hydrogen is going to have to come from this BH4 minus ion. This is going to produce as a byproduct BH3. So I ask myself, where are the electrons for this coming from? Well, the only place they could be coming from is from this BH sigma bond. So it's really the electrons in this bond that are getting shared with that central carbon. And at the same time, that's going to break the pi bond to oxygen. And then in the subsequent step, that oxygen needs to grab a hydrogen from my solvent. So in the end, there are two byproducts to this, BH3 and this, what we would call ethoxide ion. So that's that reduction reaction. This oxidation reaction, I don't require students to even learn this mechanism in my summer course. The different courses might require you to know it, but it's a little weird because it involves the chromium. But given that I've drawn everything out, you could probably draw the curved arrows for this. So in the first step, you see that oxygen is going to bond to chromium. Oxygen has the electrons to do that, so it's going to share the electrons with chromium. That's going to make that oxygen chromium bond. Then I see I have an extra hydrogen, an extra proton that I'm going to need to remove. So I'm going to deprotonate that intermediate. And in the next step, I'm going to protonate the oxygen on the other side. And now the last step. This last step is pretty tricky, but it's important to notice that I need to remove a hydrogen from my central carbon. And I need to break off that chromium compound. And so how am I going to do that? Well, it's water that's going to come grab the hydrogen. So water is going to share its lone pair with hydrogen. I need to break this carbon-hydrogen bond and form the carbon-oxygen double bond. I then need to break the oxygen-chromium bond. Notice that's going to become this lone pair here. And in the end, I notice I have chromium with only one double bond to oxygen. That means this other double bond to oxygen is going out onto the oxygen. That's what gives the other oxygen a negative charge. Weird mechanism, not one I would expect you to predict. And like I said, even in my college course, I don't ask students to memorize how this mechanism works. But for practice, you can draw the curved arrows. And notice in this case, I get this byproduct. And the solution is actually going to become acidic because I've also created H3O plus as a byproduct. So there's an example of some oxidation reduction mechanisms. The key thing to note, they go by entirely different mechanisms and use entirely different reagents. So now that we've done some practice with the mechanisms, the last step is to start to identify when oxidation and or reduction is taking place. So the last two slides are going to be about identifying whether oxidation or reduction or neither is happening in a reaction. Okay, so our last step is going to be to look at some reactions, identify oxidation levels, and see how they're changing. So I've started by giving you a couple examples where oxidation is happening. So let's talk about how we could figure that out. So in my first case, this first reactant, my central carbon, has one bond to a more electronegative atom. So, if I'm tracking oxidation levels, I'll do that in red here. This oxidation level is 1 because there's one bond from carbon to oxygen. And then in the product, there are 2 bonds from carbon to oxygen. So oxidation level is going up. That's why it's an example of oxidation. In the second case, I've got to remember that when I have the pi bond in this alkene between 2 carbons, so a pi bond between carbons is going to count as 1/2 oxidation level for each. So each of those carbons is 1/2, whereas in the product, each of those carbons has one bond to oxygen. So each of them is oxidation level 1. So in this second case, an oxidation has occurred. I've gone from level 1/2 to 1 for each carbon, or from overall level 1 to overall level 2. So those are examples of oxidation. How about reduction? So in this case, I've got 2 oxygens, each with an oxidation level of 1. You might remember this functional group's called an epoxide. So each of those has an oxidation level of 1. Now in my product, I only have one carbon with an oxidation level of 1. The neighboring carbon now has an oxidation level of 0. So it has been reduced. So that's an example of a reduction. It's also an example of reduction if I take my alkyne, where we said each of those carbons, because it has 2 pi bonds to another carbon, is oxidation level 1, whereas in the alkene product, each of them has an oxidation level of 1/2. So those have been reduced. So that's a reduction reaction. And then there are examples where the oxidation level isn't changing. So when I have an alkene, each of these is at 1/2. So my total level is 1. If I make an alcohol as a product, notice now my oxidation level for one of those carbons has gone from 1/2 to 1. The other one has gone from 1/2 to 0. So the total is still equal to 1. So this reaction wouldn't be oxidation or reduction. This next case, if I start with an alkyl halide, it's got 1 bond to a more electronegative atom. And I make an alcohol that also has 1 bond to a more electronegative atom. That's a lateral move. It's not increasing or decreasing the oxidation level. So the last step, I want you to practice on your own, assigning oxidation levels to each carbon atom in the compounds, and then you can decide if the reaction is an oxidation, a reduction, or neither. So I want you to pause and go ahead and do that, and then you can check your answers. Okay, let's cap off this Module 14 lecture about oxidation levels. Hopefully you have gone through and tried this out yourself. In this first case, I'm going to just put oxidation levels next to each atom. So oxidation level of this carbon is bonded to 2 more electronegative atoms, two bonds to oxygen. So it's got an oxidation level of 2. When I go to its neighbor, that's got a pi bond, so that's going to be 1/2. Each of these is going to be 1/2 because each of them has a pi bond to another carbon. And then in this other compound, this one's going to be 1 because it's got 1 bond to nitrogen. This one's going to be 0. Now I look at the product, and all of these in the ring have stayed at 1/2. So nothing's changed there. I look at this carbon here, still got 2 bonds to a more electronegative atom. In this case, it's nitrogen instead of oxygen, but that's still an oxidation level of 2. This carbon over here still has an oxidation level of 1, and this one has an oxidation level of 0. Nothing has changed. So this is neither. If I look at the next one, I've got several carbons with an oxidation level of 0, but then I have 1/2 here for each of these alkene carbons. And in my product, everything is 0. So this would be a reduction. In my next example, carbon starts with 3 bonds to nitrogen. That's oxidation level of 3. And the other 2 carbons here have an oxidation level of 0. In my product, this is 0, this is 0, but this is also 3. So nothing has changed. This is neither. All right, in this next example, I've got oxidation level 1/2 for each of my alkene carbons. And then this one over here on the end is 0. after the reaction, I still have 1/2 here, 1/2 here, but now this one has an oxidation level of 1, so this is an oxidation. My last one here, hopefully you can see that we have a lot of atoms at oxidation level of 0 and 1 carbon atom with an oxidation level of 1. And in the product, we have the same thing. So this would be an example of neither. All right, and that is our overview of oxidation and reduction, just getting you used to the language that chemists use. And let me know what questions you have.